Hi everyone. So today we are going to be continuing our Zero to Hero series, and in particular, today we are going to reproduce the GPT-2 model, the 124 million version of it. So when OpenAI released GPT-2, this was 2019, and they released it with this blog post. On top of that, they released this paper, and on top of that, they released this code on GitHub. So OpenAI/GPT-2. Now, when we talk about reproducing GPT-2, we have to be careful because in particular in this video, we're going to be reproducing the 124 million parameter model. So the thing to realize is that there's always a mini-series when these releases are made. So there are the GPT-2 mini-series made up of models at different sizes, and usually the biggest model is called the GPT-2. But basically the reason we do that is because you can put the model sizes on the x-axis of plots like this, and on the y-axis, you put a lot of downstream metrics that you're interested in, like translation, summarization, question answering, and so on. And you can chart out these scaling laws. Basically, as the model size increases, you're getting better and better at downstream metrics. And so in particular for GPT-2, if we scroll down in the paper, there are 4 models in the GPT-2 mini-series, starting at 124 million all the way up to 1,558 million. Now, the reason my numbers, the way I say them, disagree with this table is that this table is wrong. If you actually go to the GPT-2 GitHub repo, they sort of say that there was an error in how they added up the parameters, but basically this is the 124 million parameter model, etc. So the 124 million parameter had 12 layers in the transformer, and it had 768 channels in the transformer, 768 dimensions. And I'm going to be assuming some familiarity with what these terms mean because I covered all of this in my previous video, Let's Build GPT from Scratch. So I covered that in the previous video in this playlist. Now, if we do everything correctly and everything works out well, by the end of this video, we're going to see something like this, where we're looking at the validation loss, which basically measures how good we are at predicting the next token in a sequence on some validation data that the model has not seen during training. And we see that we go from doing that task not very well, because we're initializing from scratch, all the way to doing that task quite well by the end of the training. And hopefully we're going to beat the GPT-2 124M model. Now, previously when they were working on this is already 5 years ago. So this was probably a fairly complicated optimization at the time, and the GPUs and the compute was a lot smaller. Today, you can reproduce this model in roughly an hour, or probably less even, and it will cost you about $10 if you want to do this on the cloud compute, a sort of computer that you can all rent. And if you pay $10 for that computer, you wait about an hour or less, you can actually achieve a model that is as good as this model that OpenAI released. And one more thing to mention is, unlike many other models, OpenAI did release the weights for GPT-2. So those weights are all available in this repository. But the GPT-2 paper is not always as good with all of the details of training. So in addition to the GPT-2 paper, we're going to be referencing the GPT-3 paper, which is a lot more concrete in a lot of the hyperparameters and optimization settings and so on. And it's not a huge departure in the architecture from the GPT-2 version of the model. So we're going to be referencing both GPT-2 and GPT-3 as we try to reproduce GPT-2 124M. So let's go. So the first thing I would like to do is actually start at the end, or at the target. So in other words, let's load the GPT-2 124M model as it was released by OpenAI and maybe take it for a spin. Let's sample some tokens from it. Now, the issue with that is when you go to the code base of GPT-2 and you go into the source and you click in on the model.py, you'll realize that actually this is using TensorFlow. So the original GPT-2 code here was written in TensorFlow, which is, let's just say not used as much anymore. So we'd like to use PyTorch because it's a lot friendlier, easier, and I just personally like it a lot more. The problem with that is the initial code is in TensorFlow. We'd like to use PyTorch. So instead, to get the target, we're going to use the Hugging Face Transformers code, which I like a lot more. So when you go into the Transformers source, Transformers models, GPT-2 modeling, GPT-2.py, you will see that they have the GPT-2 implementation of that transformer here in this file. And it's like medium readable, but not fully readable. But what it does is it did all the work of converting all those weights from TensorFlow to PyTorch friendly, and so it's much easier to load and work with. So in particular, we can look at the GPT-2 model here, and we can load it using Hugging Face transformers. So swinging over, this is what that looks like. From transformers, import the GPT-2 LM head model, and then from pre-trained GPT-2. Now, one awkward thing about this is that when you do GPT-2 as the model that we're loading, this actually is the 124 million parameter model. If you want the GPT-2, the 1.5 billion, then you actually want to do -XL. So this is the 124M, our target. Now what we're doing is when we actually get this, we're initializing the PyTorch NN module as defined here in this class. From it, I want to get just the state dict, which is just the raw tensors. So we just have the tensors of that file. And by the way, here, this is a Jupyter Notebook, but this is Jupyter Notebook running inside VS Code. So I like to work with it all in a single sort of interface. So I like to use VS Code. So this is the Jupyter Notebook extension inside VS Code. So when we get the state dict, this is just a dict. So we can print the key and the value, which is the tensor. And let's just look at the shapes. So these are sort of the different parameters inside the GPT-2 model and their shape. So the W weight for token embedding is of size 50,257 by 768. Where this is coming from is that we have 50,257 tokens in the GPT-2 vocabulary. And the tokens, by the way, these are exactly the tokens that we've spoken about in the previous video on my tokenization series. So the previous videos just before this, I go into a ton of detail on tokenization. GPT-2 tokenizer happens to have this many tokens. For each token, we have a 768 dimensional embedding that is the distributed representation that stands in for that token. So each token is a little string piece, and then these 768 numbers are the vector that represents that token. And so this is just our lookup table for tokens. And then here we have the lookup table for the positions. So because GPT-2 has a maximum sequence length of 1024, we have up to 1024 positions that each token can be attending to in the past. And every one of those positions in GPT-2 has a fixed vector of 768 that is learned by optimization. And so this is the position embedding and the token embedding. And then everything here is just the other weights and biases and everything else of this transformer. So when you just take, for example, the positional embeddings and flatten it out and take just the 20 elements, you can see that these are just the parameters. These are weights, floats, we can take and we can plot them. So these are the position embeddings. And we get something like this, and you can see that this has structure. And it has structure because what we have here really is every row in this visualization is a different position, a fixed absolute position in the range from 0 to 1024. And each row here is the representation of that position. And so it has structure because these positional embeddings end up learning these sinusoids and cosines that sort of like represent each of these positions. And each row here stands in for that position and is processed by the transformer to recover all the relative positions and sort of realize which token is where and attend to them depending on their position, not just their content. So when we actually just look into an individual column inside these, and I just grabbed 3 random columns, you'll see that, for example, here we are focusing on every single channel, and we're looking at what that channel is doing as a function of position from 0 to 1023, really. And we can see that some of these channels basically like respond more or less to different parts of the position spectrum. So this green channel really likes to fire for everything after 200 up to 800, but not less, but a lot less, and has a sharp drop off here near 0. So who knows what these embeddings are doing and why they are the way they are. You can tell, for example, that because they're a bit more jagged and they're kind of noisy, you can tell that this model was not fully trained. And the more trained this model was, the more you would expect to smooth this out. And so this is telling you that this is a little bit of an under-trained model. But in principle, actually, these curves don't even have to be smooth. This should just be totally random noise. And in fact, in the beginning of the optimization, it is complete random noise because this position embedding table is initialized completely at random. So in the beginning, you have jaggedness, and the fact that you end up with something smooth is already kind of impressive, that just falls out of the optimization. Because in principle, you shouldn't even be able to get any single graph out of this that makes sense. But we actually get something that looks a little bit noisy, but for the most part looks sinusoidal-like. In the original transformer paper, the attention is all you need paper, the positional embeddings are actually initialized and fixed, if I remember correctly, to sinusoids and cosines of different frequencies. And that's the positional encoding, and it's fixed. But in GPT-2, these are just parameters, and they're trained from scratch, just like any other parameter. And that seems to work about as well. And so what they do is they kind of like recover these sinusoidal-like features during the optimization. We can also look at any of the other matrices here. So here I took the first layer of the transformer and looking at like one of its weights and just the first block of 300 by 300. And you see some structure, but like, again, like who knows what any of this is. If you're into mechanistic interpretability, you might get a real kick out of trying to figure out like what is going on, what is this structure, and what does this all mean? But we're not going to be doing that in this video. But we definitely see that there's some interesting structure, and that's kind of cool. What we're mostly interested in is we've loaded the weights of this model that was released by OpenAI. And now using the Hugging Face transformers, we can not just get all the raw weights, but we can also get the what they call pipeline and sample from it. So this is the prefix, hello, I'm a language model, comma, and then we're sampling 30 tokens, and we're getting 5 sequences, and I ran this, and this is what it produced. Hello, I'm a language model, but what I'm really doing is making a human readable document. There are other languages, but those are ... So you can read through these if you like, but basically these are 5 different completions of the same prefix from this GPT-2 124M. Now, if I go here, I took this example from here, and sadly, even though we are fixing the seed, we are getting different generations from the snippet than what they got. So presumably the code changed. But what we see though at this stage that's important is that we are getting coherent text. So we've loaded the model successfully. We can look at all its parameters, and the keys tell us where in the model these come from. And we want to actually write our own GPT-2 class so that we have full understanding of what's happening there. We don't want to be working with something like the modeling GPT-2.py because it's just too complicated. We want to write this from scratch ourselves. So we're going to be implementing the GPT model here in parallel. And as our first task, let's load the GPT-2 124M into the class that we're going to develop here from scratch. That's going to give us confidence that we can load the OpenAI model, and therefore there's a setting of weights that exactly is the 124 model. But then of course what we're going to do is we're going to initialize the model from scratch instead and try to train it ourselves on a bunch of documents that we're going to get. And we're going to try to surpass that model. So we're going to get different weights and everything's going to look different, hopefully better even. But we're going to have a lot of confidence that because we can load the OpenAI model, we are in the same model family and model class, and we just have to rediscover a good setting of the weights, but from scratch. So let's now write the GPT-2 model, and let's load the weights and make sure that we can also generate text that looks coherent. Okay, so let's now swing over to the attention is all you need paper that started everything, and let's scroll over to the model architecture, the original transformer. Now, remember that GPT-2 is slightly modified from the original transformer. In particular, we do not have the encoder. GPT-2 is a decoder-only transformer, as we call it. So this entire encoder here is missing. And in addition to that, this cross-attention here that was using that encoder is also missing. So we delete this entire part. Everything else stays almost the same, but there are some differences that we're going to sort of look at here. So there are 2 main differences. When we go to the GPT-2 paper under 2.3.model, we notice that first, there's a reshuffling of the layer norms, so they change place. And second, an additional layer normalization was added here to the final self-attention block. So basically, all the layer norms here, instead of being after the MLP or after the attention, they swing before it, and an additional layer norm gets added here right before the final classifier. So now let's implement some of the first sort of skeleton NN modules here in our GPT NN module. And in particular, we're going to try to match up this schema here that is used by Hugging Face transformers, because that will make it much easier to load these weights from this state dict. So we want something that reflects this schema here. So here's what I came up with. Basically, we see that the main container here that has all the modules is called transformer. So I'm reflecting that with an NN module dict. And this is basically a module that allows you to index into the submodules using keys, just like a dictionary, strings. Within it, we have the weights of the token embeddings, WTE, and that's an NN embedding, and the weights of the position embeddings, which is also just an NN embedding. And if you remember, NN embedding is really just a fancy little wrapper module around just a single array of numbers, a single block of numbers, just like this. It's a single tensor. And NN embedding is a glorified wrapper around a tensor that allows you to access its elements by indexing into the rows. Now, in addition to that, we see here that we have a .h, and then this is indexed using numbers instead of indexed using strings. So there's a .h, .0, 1, 2, etc., all the way up till .h.11. And that's because there are 12 layers here in this transformer. So to reflect that, I'm creating also an h, I think that probably stands for hidden. And instead of a module dict, this is a model list. So we can index it using integers exactly as we see here, .0, .1, 2, etc. And the module list has n layer blocks, and the blocks are yet to be defined in a module in a bit. In addition to that, following the GPT-2 paper, we need an additional final layer norm that we're going to put in there. And then we have the final classifier, the language model head, which projects from 768, the number of embedding dimensions in this GPT, all the way to the vocab size, which is 50,257, and GPT-2 uses no bias for this final sort of projection. So this is the skeleton, and you can see that it reflects this. So the WTE is the token embeddings. Here it's called output embedding, but it's really the token embeddings. The PE is the positional encodings. Those two pieces of information, as we saw previously, are going to add and then go into the transformer. The .h is all the blocks in gray, and the LNF is this new layer that gets added here by the GPT-2 model. And LM head is this linear part here. So that's the skeleton of the GPT-2. We now have to implement the block. Okay, so let's now recurse to the block itself. So we want to define the block. So I'll start putting them here. So the block, I like to write out like this. These are some of the initializations, and then this is the actual forward pass of what this block computes. And notice here that there's a change from the transformer again that is mentioned in the GPT-2 paper. So here, the layer normalizations are after the application of attention or feed forward. In addition to that, note that the normalizations are inside the residual stream. You see how feed forward is applied and then this arrow goes through and through the normalization. So that means that your residual pathway has normalizations inside them. And this is not very good or desirable. You actually prefer to have a single clean residual stream all the way from supervision, all the way down to the inputs, the tokens. And this is very desirable and nice because the gradients that flow from the top, if you remember from your micrograd, addition just distributes gradients during the backward stage to both of its branches equally. So addition is a branch in the gradients. And so that means that the gradients from the top flow straight to the inputs, the tokens, through the residual pathways unchanged. But then in addition to that, the gradient also flows through the blocks, and the blocks contribute their own contribution over time and kick in and change the optimization over time. But basically, clean residual pathway is desirable from an optimization perspective. And then this is the pre-normalization version, where you see that Rx first goes through the layer normalization and then the attention, and then goes back out to go to the layer normalization number 2 and the multi-layer perceptron, sometimes also referred to as a feed-forward network or an FFN. And then that goes into the residual stream again. And the one more thing that is kind of interesting to note is that recall that attention is a communication operation. It is where all the tokens, and there's 1024 tokens lined up in a sequence. And this is where the tokens communicate. This is where they exchange information. So attention is a aggregation function. It's a pooling function. It's a weighted sum function. It is a reduce operation. Whereas MLP, this MLP here happens at every single token individually. There's no information being collected or exchanged between the tokens. So the attention is the reduce and the MLP is the map. And what you end up with is that the transformer ends up just being a repeated application of map reduce, if you want to think about it that way. So this is where they communicate, and this is where they think individually about the information that they gathered. And every one of these blocks iteratively refines the representation inside the residual stream. So this is our block, slightly modified from this picture. Okay, so let's now move on to the MLP. So the MLP block, I implemented it as follows. It is relatively straightforward. We basically have two linear projections here that are sandwiched in between the Gelu nonlinearity. So nn.gelu approximate is 10h. Now when we swing over to the PyTorch documentation, this is n.gelu, and it has this format, and it has two versions: the original version of Gelu, which we'll step into in a bit, and the approximate version of Gelu, which we can request using 10h. So as you can see, just as a preview here, Gelu is basically like a ReLU, except there's no exactly flat tail here at exactly 0. But otherwise it looks very much like a slightly smoother ReLU. It comes from this paper here, Gaussian error linear units. And you can step through this paper, and there's some mathematical kind of like reasoning that leads to an interpretation that leads to the specific formulation. It has to do with stochastic regularizers and the expectation of a modification to adaptive dropout. So you can read through all of that if you'd like here. And there's a little bit of a history as to why there's an approximate version of Gelu, and that comes from this issue here, as far as I can tell. And in this issue, Daniel Hendricks mentions that at the time when they developed this nonlinearity, the earth function, which you need to evaluate the exact Gelu, was very slow in TensorFlow, so they ended up basically developing this approximation. And this approximation that then ended up being picked up by BERT and by GPT-2, etc. But today there's no real good reason to use the approximate version. You'd prefer to just use the exact version, because my expectation is that there's no big difference anymore. And this is kind of like a historical kind of quirk. But we are trying to reproduce GPT-2 exactly, and GPT-2 used the 10h approximate version, so we prefer to stick with that. Now, one other reason to actually just intuitively use Gelu instead of ReLU is previously in videos in the past, we've spoken about the dead ReLU neuron problem, where in this tail of a ReLU, if it's exactly flat at 0, any activations that fall there will get exactly 0 gradient. There's no change, there's no adaptation, there's no development of the network if any of these activations end in this flat region. But the Gelu always contributes a local gradient, and so there's always going to be a change, always going to be an adaptation, and sort of smoothing it out ends up empirically working better in practice, as demonstrated in this paper, and also as demonstrated by it being picked up by the BERT paper, GPT-2 paper, and so on. So for that reason, we adopt this nonlinearity here in the GPT-2 reproduction. Now, in more modern networks, also like Llama 3 and so on, this nonlinearity also further changes to Swiglu and other variants like that. But for GPT-2, they use this approximate Gelu. Okay, and finally, we have the attention operation. So let me paste in my attention. So I know this is a lot, so I'm gonna go through this a bit slowly, but not too slowly, because we have covered this in the previous video, and I would just point you there. So this is the attention operation. Now, in the previous video, you will remember, this is not just attention, this is multi-headed attention, right? And so in the previous video, we had this multi-headed attention module, and this implementation made it obvious that these heads are not actually that complicated. There's basically, in parallel, inside every attention block, there's multiple heads, and they're all functioning in parallel, and their outputs are just being concatenated, and that becomes the output of the multi-headed attention. So the heads are just kind of like parallel streams, and their outputs get concatenated. And so it was very simple and made the head be kind of like fairly straightforward in terms of its implementation. What happens here is that instead of having two separate modules, and indeed many more modules that get concatenated, all of that is just put into a single self-attention module. And instead, I'm being very careful and doing a bunch of transpose, split tensor gymnastics to make this very efficient in PyTorch. But fundamentally and algorithmically, nothing is different from the implementation we saw before in this Git repository. So to remind you very briefly, and I don't want to go into this in too much time, but we have these tokens lined up in a sequence, and there's 1020 of them. And then each token at this stage of the attention emits three vectors: the query, key, and the value. And first what happens here is that the queries and the keys have to multiply each other to get sort of the attention amount, like how interesting they find each other. So they have to interact multiplicatively. So what we're doing here is we're calculating the QKV, we're splitting it, and then there's a bunch of gymnastics as I mentioned here. And the way this works is that we're basically making the number of heads, nh, into a batch dimension. And so it's a batch dimension just like B, so that in these operations that follow, PyTorch treats B and nh as batches, and it applies all the operations on all of them in parallel, in both the batch and the heads. And the operations that get applied are, number one, the queries and the keys interact to give us our attention. This is the autoregressive mask that makes sure that the tokens only attend to tokens before them and never to tokens in the future. The softmax here normalizes the attention, so it sums to 1 always. And then recall from the previous video that doing the attention matrix multiply with the values is basically a way to do a weighted sum of the values of the tokens that we found interesting at every single token. And then the final transpose, contiguous, and view is just reassembling all of that again, and this actually performs the concatenation operation. So you can step through this slowly if you'd like, but it is equivalent mathematically to our previous implementation. It's just more efficient in PyTorch, so that's why I chose this implementation instead. Now, in addition to that, I'm being careful with how I name my variables. So for example, caten is the same as caten, and so actually our keys should basically exactly follow the schema of the Hugging Face Transformers code, and that will make it very easy for us to now port over all the weights from exactly this sort of naming conventions, because all of our variables are named the same thing. But at this point, we have finished the GPT-2 implementation, and what that allows us to do is we don't have to basically use this file from Hugging Face, which is fairly long. This is 2,000 lines of code. Instead, we just have less than 100 lines of code, and this is the complete GPT-2 implementation. So at this stage, we should just be able to take over all the weights, set them, and then do generation. So let's see what that looks like. Okay, so here I've also changed the GPT config so that the numbers here, the hyperparameters, agree with the GPT-2 124M model. So the maximum sequence length, which I call block size here, is 124. The number of tokens is 257, which if you watch my tokenizer video know that this is 50,000 merges, BPE merges, 256 byte tokens, the leaves of the BPE tree, and one special end of text token that delimits different documents and can start generation as well. And there are 12 layers, there are 12 heads in the attention, and the dimension of the transformers was 768. So here's how we can now load the parameters from Hugging Face to our code here and initialize the GPT class with those parameters. So let me just copy paste a bunch of code here. And I'm not going to go through this code too slowly, because honestly, it's not that interesting. It's not that exciting. We're just loading the weights, so it's kind of dry. But as I mentioned, there are 4 models in this mini series of GPT-2. This is some of the Jupyter code that we had here on the right. I'm just porting it over. These are the hyperparameters of the GPT-2 models. We're creating the config object and creating our own model. And then what's happening here is we're creating the state dict, both for our model and for the Hugging Face model. And then what we're doing here is we're going over the Hugging Face model keys, and we're copying over those tensors. And in the process, we are kind of ignoring a few of the buffers. They're not parameters, they're buffers. So for example, attention.bias, that's just used for the autoregressive mask. And so we are ignoring some of those masks, and that's it. And then one additional kind of annoyance is that this comes from the TensorFlow repo, and I'm not sure how, this is a little bit annoying, but some of the weights are transposed from what PyTorch would want. And so manually I hard-coded the weights that should be transposed, and then we transpose them if that is so. And then we return this model. So the from pre-trained is a constructor or a class method in Python that returns the GPT object if we just give it the model type, which in our case is GPT-2, the smallest model that we're interested in. So this is the code, and this is how you would use it. And we can pop open the terminal here in VS Code, and we can Python train GPT-2.py, and fingers crossed. Okay, so we didn't crash. And so we can load the weights and the biases and everything else into our NN module. But now let's also get additional confidence that this is working, and let's try to actually generate from this model. Okay, now before we can actually generate from this model, we have to be able to forward it. We didn't actually write that code yet. So here's the forward function. So the input to the forward is going to be our indices, our tokens, token indices. And they are always of shape b by t. And so we have batch dimension of b, and then we have the time dimension of up to t. And the t can't be more than the block size. The block size is the maximum sequence length. So b by t indices arranged as sort of like a two-dimensional layout. And remember that basically every single row of this is of size up to block size. And this is t tokens that are in a sequence. And then we have b independent sequences stacked up in a batch so that this is efficient. Now, here we are forwarding the position embeddings and the token embeddings. And this code should be very recognizable from the previous lecture. So we basically use arrange, which is kind of like a version of range, but for PyTorch. And we're iterating from 0 to t and creating this positions sort of indices. And then we are making sure that they're on the same device as IDX, because we're not going to be training on only CPU. That's going to be too inefficient. We want to be training on GPU, and that's going to come in a bit. Then we have the position embeddings and the token embeddings, and the addition operation of those two. Now notice that the position embeddings are going to be identical for every single row of input. And so there's broadcasting hidden inside this plus, where we have to create an additional dimension here, and then these two add up, because the same position embeddings apply at every single row of our examples stacked up in a batch. Then we forward the transformer blocks, and finally the last layer norm and the LM head. So what comes out after forward is the logits. And if the input was b by t indices, then at every single b by t, we will calculate the logits for what token comes next in the sequence. So what is the token b t plus 1? The one on the right of this token. And vocab size here is the number of possible tokens. And so therefore this is the tensor that we're going to obtain. And these logits are just a softmax away from becoming probabilities. So this is the forward pass of the network. And now we can get logits. And so we're going to be able to generate from the model imminently. Okay, so now we're going to try to set up the identical thing on the left here that matches Hugging Face on the right. So here we've sampled from the pipeline, and we sampled 5 times up to 30 tokens with the prefix of hello, I'm a language model. And these are the completions that we achieved. So we're going to try to replicate that on the left here. So number return sequences is 5, max length is 30. So the first thing we do, of course, is we initialize our model. Then we put it into evaluation mode. Now, this is a good practice to put the model into eval when you're not going to be training it. You're just going to be using it. And I don't actually know if this is doing anything right now for the following reason. Our model up above here contains no modules or layers that actually have a different behavior at training or evaluation time. So for example, dropout, batch norm, and a bunch of other layers have this kind of behavior. But all of these layers that we've used here should be identical in both training and evaluation time. So potentially model.eval does nothing, but then I'm not actually sure if this is the case, and maybe PyTorch internals do some clever things depending on the evaluation mode inside here. The next thing we're doing here is we are moving the entire model to CUDA. So we're moving all of the tensors to GPU. So I'm SSH'd here to a cloud box, and I have a bunch of GPUs on this box. And here I'm moving the entire model and all of its members and all of its tensors and everything like that, everything gets shipped off to basically a whole separate computer that is sitting on the GPU. And the GPU is connected to the CPU, and they can communicate, but it's basically a whole separate computer with its own computer architecture, and it's really well catered to parallel processing tasks like those of running neural networks. So I'm doing this so that the model lives on the GPU, a whole separate computer, and it's just going to make our code a lot more efficient because all of this stuff runs a lot more efficiently on the GPUs. So that's the model itself. Now, the next thing we want to do is we want to start with this as the prefix when we do the generation. So let's actually create those prefix tokens. So here's the code that I've written. We're going to import the tick token library from OpenAI, and we're going to get the GPT-2 encoding. So that's the tokenizer for GPT-2. And then we're going to encode this string and get a list of integers, which are the tokens. Now these integers here should actually be fairly straightforward because we can just copy paste this string and we can sort of inspect what it is in tick tokenizer. So just pasting that in, these are the tokens that are going to come out. So this list of integers is what we expect tokens to become. And as you recall, if you saw my video, of course, all the tokens, they're just little string chunks, right? So this is the chuncation of this string into GPT-2 tokens. So once we have those tokens, it's a list of integers, we can create a torch tensor out of it. In this case, it's 8 tokens. And then we're going to replicate these 8 tokens for 5 times to get 5 rows of 8 tokens. And that is our initial input x, as I call it here. And it lives on the GPU as well. So x now is this IDX that we can put into forward to get our logits so that we know what comes as the 6th token, as the 9th token in every one of these 5 rows. Okay, and we are now ready to generate. So let me paste in one more code block here. So what's happening here in this code block is we have this x, which is of size b by t, right? So batch by time. And we're going to be, in every iteration of this loop, we're going to be adding a column of new indices into each one of these rows, right? And so these are the new indices, and we're appending them to the sequence as we're sampling. So with each loop iteration, we get one more column into X. And all of the operations happen in the context manager of torch.nograd. This is just telling PyTorch that we're not going to be calling .backward on any of this. So it doesn't have to cache all the intermediate tensors. It's not going to have to prepare in any way for a potential backward later. And this saves a lot of space and also possibly some time. So we get our logits. We get the logits at only the last location. We throw away all the other logits. We don't need them. We only care about the last column's logits. So this is being wasteful, but this is just kind of like an inefficient implementation of sampling. So it's correct, but inefficient. So we get the last column of logits, pass it through softmax to get our probabilities. Then here I'm doing top case sampling of 50, and I'm doing that because this is the Hugging Face default. So just looking at the Hugging Face docs here of a pipeline, there's a bunch of quarks that go into Hugging Face, and I mean, it's kind of a lot, honestly, but I guess the important one that I noticed is that they're using top K by default, which is 50. And what that does is that, so that's being used here as well. And what that does is basically we want to take our probabilities and we only want to keep the top 50 probabilities. And anything that is lower than the 50th probability, we just clamp to 0 and renormalize. And so that way we are never sampling very rare tokens. The tokens we're going to be sampling are always in the top 50 of most likely tokens. And this helps keep the model kind of on track, and it doesn't blabber on and it doesn't get lost and doesn't go off the rails as easily. And it kind of like sticks in the vicinity of likely tokens a lot better. So this is the way to do it in PyTorch, and you can step through it if you like. I don't think it's super insightful, so I'll speed through it. But roughly speaking, we get this new column of tokens. We append them on X, and basically the columns of X grow until this while loop gets stripped up. And then finally, we have an entire X of size 5 by 30 in this case, in this example, and we can just basically print all those individual rows. So I'm getting all the rows, I'm getting all the tokens that were sampled, and I'm using the decode function from tick tokenizer to get back the string, which we can print. And so terminal, new terminal, and let me Python train GPT-2. Okay, so these are the generations that we're getting. Hello, I'm a language model, not a program. New line, etc. Hello, I'm a language model, and one of the main things that bothers me when they create languages is how easy it becomes to create something that I mean, so this will just like blabber on, right, in all these cases. Now, one thing you will notice is that these generations are not the generations of Hugging Face here. And I can't find the discrepancy, to be honest, and I didn't fully go through all these options, but probably there's something else hiding in addition to the top P. So I'm not able to match it up, but just for correctness, down here below in the Jupyter Notebook, and using the Hugging Face model, so this is the Hugging Face model here, I replicated the code, and if I do this and I run that, then I am getting the same results. So basically, the model internals are not wrong. It's just I'm not 100% sure what the pipeline does in Hugging Face, and that's why we're not able to match them up. But otherwise, the code is correct, and we've loaded all the tensors correctly. So we're initializing the model correctly, and everything here works. So long story short, we've ported all the weights. We initialize the GPT-2. This is the exact OpenAI GPT-2, and it can generate sequences, and they look sensible. And now, here, of course, we're initializing with GPT-2 model weights. But now we want to initialize from scratch, from random numbers. And we want to actually train a model that will give us sequences as good as or better than these ones in quality. And so that's what we turn to next. So it turns out that using the random model is actually fairly straightforward because PyTorch already initializes our model randomly and by default. So when we create the GPT model in the constructor, this is all of these layers and modules have random initializers that are there by default. So when these linear layers get created and so on, there's default constructors, for example, using the Javier initialization that we saw in the past to construct the weights of these layers. And so creating a random model instead of a GPT-2 model is actually fairly straightforward. And we would just come here and instead we would create model equals GPT. And then we want to use the default config, GPT config. And the default config uses the 124M parameters. So this is the random model initialization. And we can run it. And we should be able to get results. Now the results here, of course, are total garbage garble. And that's because this is a random model. And so we're just getting all these random token string pieces chunked up totally at random. So that's what we have right now. Now, one more thing I wanted to point out, by the way, is in case you do not have CUDA available because you don't have a GPU, you can still follow along with what we're doing here to some extent. And probably not to the very end, because by the end, we're going to be using multiple GPUs and actually doing a serious training run. But for now, you can actually follow along decently okay. So one thing that I like to do in PyTorch is I like to auto-detect the device that is available to you. So in particular, you could do that like this. So here we are trying to detect the device to run on that has the highest compute capability. You can think about it that way. So by default, we start with CPU, which of course is available everywhere because every single computer will have a CPU. But then we can try to detect, do you have a GPU? If so, use a CUDA. And then if you don't have a CUDA, do you at least have MPS? MPS is the backend for Apple Silicon. So if you have a MacBook that is fairly new, you probably have Apple Silicon on the inside. And then that has a GPU that is actually fairly capable, depending on which MacBook you have. And so you can use MPS, which will be potentially faster than CPU. And so we can print the device here. Now, once we have the device, we can actually use it in place of CUDA. So we just swap it in. And notice that here, when we call model on X, if this X here is on CPU instead of GPU, then it will work fine because here in the forward, which is where PyTorch will come, when we created pose, we were careful to use the device of IDX to create this tensor as well. And so there won't be any mismatch where one tensor is on CPU, one is on GPU, and that you can't combine those. But here we are carefully initializing on the correct device as indicated by the input to this model. So this will auto-detect device. For me, this will be, of course, GPU. So using device CUDA. But you can also run with, as I mentioned, another device. And it's not going to be too much slower. So if I override device here, oops, if I override device equals CPU, then we'll still print CUDA, of course, but now we're actually using CPU. 1, 2, 3, 4, 5, 6. Okay, about 6 seconds. And actually, we're not using torch compile and stuff like that, which will speed up everything a lot faster as well. But you can follow along even on the CPU, I think, to a decent extent. So that's a note on that. Okay, so I do want to loop around eventually into what it means to have different devices in PyTorch and what it is exactly that PyTorch does in the background for you when you do something like module.to device, or where you take a torch tensor and do a .to device, and what exactly happens and how that works. But for now, I'd like to get to training, and I'd like to start training the model. And for now, let's just say the device makes code go fast. And let's go into how we can actually train the model. So to train the model, we're going to need some data set. And for me, the best debugging, simplest data set that I like to use is the Tiny Shakespeare dataset. And it's available at this URL, so you can wget it, or you can just search Tiny Shakespeare dataset. And so I have it in my file system as just lsinput.txt. So I already downloaded it. And here I'm reading the dataset, getting the first 1,000 characters, and printing the first 100. Now remember that GPT-2 has roughly a compression ratio, the tokenizer has a compression ratio of roughly 3 to 1. So 1,000 characters is roughly 300 tokens here that will come out of this in the slice that we're currently getting. So this is the first few characters. And if you want to get a few more statistics on this, we can do word count on input.txt. So we can see that this is 40,000 lines, about 200,000 words in this dataset, and about 1 million bytes in this file. And knowing that this file is only ASCII characters, there's no crazy Unicode here as far as I know. And so every ASCII character is encoded with 1 byte. And so this is the same number, roughly 1 million characters inside this dataset. So that's the dataset size. By default, very small and minimal dataset for debugging to get us off the ground. In order to tokenize this dataset, we're going to get tick token encoding for GPT-2, encode the data, the first 1,000 characters, and then I'm only going to print the first 24 tokens. So these are the tokens as a list of integers. And if you can read GPT-2 tokens, you will see that 198 here, you'll recognize that as the slashing character. So that is a new line. And then here, for example, we have 2 new lines, so that's 198 twice here. So this is just a tokenization of the first 24 tokens. So what we want to do now is we want to actually process these token sequences and feed them into a transformer. And in particular, we want to rearrange these tokens into this IDX variable that we're going to be feeding into the transformer. So we don't want a single very long one-dimensional sequence. We want an entire batch where each sequence is up to, is basically T tokens, and T cannot be larger than the maximum sequence length. And then we have these T long sequences of tokens, and we have B independent examples of sequences. So how can we create a B by T tensor that we can feed into the forward out of these one-dimensional sequences? So here's my favorite way to achieve this. So if we take torch and then we create a tensor object out of this list of integers and just the first 24 tokens, my favorite way to do this is basically you do a dot view of for example, 4 by 6, which multiply to 24. And so it's just a two-dimensional rearrangement of these tokens. And you'll notice that when you view this one-dimensional sequence as two-dimensional 4 by 6 here, the first 6 tokens up to here end up being the first row. The next 6 tokens here end up being the second row, and so on. And so basically, it's just going to stack up every 6 tokens in this case as independent rows, and it creates a batch of tokens in this case. And so, for example, if we are token 25 in the transformer, when we feed this in and this becomes the IDX, this token is going to see these 3 tokens and is going to try to predict that 198 comes next. So in this way, we are able to create this two-dimensional batch. That's quite nice. Now, in terms of the label that we're going to need for the target to calculate the loss function, how do we get that? Well, we could write some code inside the forward pass because we know that the next token in a sequence, which is the label, is just to the right of us. But you'll notice that actually for this token at the very end, 13, we don't actually have the next correct token because we didn't load it. So we actually didn't get enough information here. So I'll show you my favorite way of basically getting these batches. And I like to personally have not just the input to the transformer, which I like to call X, but I also like to create the labels tensor, which is of the exact same size as X, but contains the targets at every single position. And so here's the way that I like to do that. I like to make sure that I fetch +1 token, because we need the ground truth for the very last token for 13. And then when we're creating the input, we take everything up to the last token, not including, and view it as 4×6. And when we're creating the targets, we do the buffer, but starting at index 1, not index 0. So we're skipping the first element, and we view it in the exact same size. And then when I print this, here's what happens, where we see that basically, as an example for this token 25, its target was 198, and that's now just stored at the exact same position in the targets tensor, which is 198. And also, this last token 13 now has its label, which is 198, and that's just because we loaded this +1 here. So basically, this is the way I like to do it. You take long sequences, you view them in two-dimensional terms so that you get batches of time, and then we make sure to load one additional token. So we basically load a buffer of tokens of b times t plus 1, and then we sort of offset things and view them. And then we have two tensors. One of them is the input to the transformer, and the other exactly is the labels. And so let's now reorganize this code and create a very simple data loader object that tries to basically load these tokens and feed them to the transformer and calculate the loss. Okay, so I've reshuffled the code here accordingly. So as you can see here, I'm temporarily overriding to run on CPU and importing tick token, and all of this should look familiar. We're loading 1,000 characters. I'm setting BT to just be 4 and 32 right now, just because we're debugging. We just want to have a single batch that's very small. And all of this should now look familiar and follows what we did on the right. And then here we create the model and get the logits. And so here, as you see, I already ran this, only runs in a few seconds. But because we have a batch of 4×32, our logits are now of size 4×32 by 50,257. So those are the logits for what comes next at every position. And now we have the labels, which are stored in Y. So now is the time to calculate the loss, and then do the backward pass, and then do the optimization. So let's first calculate the loss. Okay, so to calculate the loss, we're going to adjust the forward function of this NN module in the model. And in particular, we're not just going to be returning logits, but also we're going to return the loss. And we're going to not just pass in the input indices, but also the targets in Y. And now we will print not logits.shape anymore. We're actually going to print the loss function. And then sys.exit of 0 so that we skip some of the sampling logic. So now let's swing up to the forward function, which gets called there, because now we also have these optional targets. And when we get the targets, we can also calculate the loss. And remember that we want to basically return logits loss, and loss by default is none, but let's put this here. If targets is not none, then we want to calculate the loss. And Copilot is already getting excited here and calculating what looks to be correct loss. It is using the cross entropy loss as is documented here. So this is a function in PyTorch under the functional. Now, what is actually happening here, because it looks a little bit scary, basically the f cross entropy does not like multidimensional inputs. It can't take a b by t by vocab size. So what's happening here is that we are flattening out this three-dimensional tensor into just 2 dimensions. The first dimension is going to be calculated automatically, and it's going to be b times t, and then the last dimension is vocab size. So basically this is flattening out this 3-dimensional tensor of logits to just be 2-dimensional b times t, all individual examples, and vocab size on in terms of the length of each row. And then it's also flattening out the targets, which are also two-dimensional at this stage, but we're going to just flatten them out. So they're just a single tensor of b times t. And this can then pass into cross entropy to calculate a loss, which we return. So this should basically, at this point, run, because this is not too complicated. So let's run it. And let's see if we should be printing the loss. And here we see that we printed 11, roughly. And so, and notice that this is the tensor of a single element, which is this number 11. Now, we also want to be able to calculate a reasonable kind of starting point for a randomly initialized network. So we covered this in previous videos, but our vocabulary size is 50,257. At initialization of the network, you would hope that every vocab element is getting roughly a uniform probability, so that we're not favoring at initialization any token way too much. We're not confidently wrong at initialization. So what we're hoping is that the probability of any arbitrary token is roughly 1 over 50,257. And now we can sanity check the loss, because remember that the cross entropy loss is just basically the negative log likelihood. So if we now take this probability and we take it through the natural logarithm, and then we do the negative, that is the loss we expect at initialization. And we covered this in previous videos. So I would expect something around 10.82, and we're seeing something around 11. So it's not way off. This is roughly the probability I expect at initialization. So that tells me that at initialization, our probability distribution is roughly diffuse. It's a good starting point, and we can now perform the optimization and tell the network which elements should follow correctly in what order. So at this point, we can do a loss.backward, calculate the gradients, and do an optimization. So let's get to that. Okay, so let's do the optimization now. So here we have the loss. This is how we get the loss. But now basically we want a little for loop here. So for I in range, let's do 50 steps or something like that. Let's create an optimizer object in PyTorch. And so here we are using the Atom optimizer, which is an alternative to the stochastic gradient descent optimizer, SGD, that we were using. So SGD is a lot simpler. Atom is a bit more involved. And I actually specifically like the Atom W variation because, in my opinion, it kind of just like fixes a bug. So Atom W is a bug fix of Atom, is what I would say. When we go to the documentation for Atom W, oh my gosh, we see that it takes a bunch of hyperparameters, and it's a little bit more complicated than the SGD we were looking at before, because in addition to basically updating the parameters with the gradient scaled by the learning rate, it keeps these buffers around, and it keeps two buffers, the M and the V, which it calls the first and the second moment. So something that looks a bit like momentum and something that looks a bit like RMS prop, if you're familiar with it. But you don't have to be. It's just kind of like a normalization that happens on each gradient element individually and speeds up the optimization, especially for language models. But I'm not going to go into the detail right here. We're going to treat it as a bit of a black box, and it just optimizes the objective faster than SGD, which is what we've seen in the previous lectures. So let's use it as a black box in our case. Create the optimizer object, and then go through the optimization. The first thing to always make sure the Copilot did not forget to zero the gradients. So always remember that you have to start with a zero gradient. Then when you get your loss and you do a dot backward adds to gradients. So it deposits gradients. It always does a plus equals on whatever the gradients are, which is why you must set them to 0. So this accumulates the gradient from this loss, and then we call the step function on the optimizer to update the parameters and to decrease the loss. And then we print the step and the loss. Dot item is used here because loss is a tensor with a single element. Dot item will actually convert that to a single float, and this float will live on the CPU. So this gets to some of the internals again of the devices, but loss is a tensor with a single element, and it lives on GPU for me because I'm using GPUs. When you call dot item, PyTorch behind the scenes will take that one-dimensional tensor, ship it back to the CPU memory, and convert it into a float that we can just print. So this is the optimization, and this should probably just work. Let's see what happens. Actually, sorry, let me, instead of using CPU override, let me delete that so this is a bit faster for me and it runs on CUDA. Oh, expected all tensors to be on the same device but found at least two devices, CUDA 0 and CPU. So CUDA 0 is the 0th GPU because I actually have 8 GPUs on this box. So the 0th GPU in my box and CPU. And model we have moved to device, but when I was writing this code, I actually introduced a bug because buff we never moved to device. And you have to be careful because you can't just do buff.to of device. It's not stateful. It doesn't convert it to be a device. It instead returns pointer to a new memory, which is on the device. So you see how we can just do model.to of device? That does not apply to tensors. You have to do buff equals buff.to device. And then this should work, okay. So what do we expect to see? We expect to see a reasonable loss in the beginning, and then we continue to optimize just a single batch. And so we want to see that we can overfit this single batch. We can crush this little batch, and we can perfectly predict the indices on just this little batch. And indeed, that is roughly what we're seeing here. So we started off at roughly 10.82, 11 in this case. And then as we continue optimizing on this single batch without loading new examples, we are making sure that we can overfit a single batch, and we are getting to very, very low loss. So the transformer is memorizing this single individual batch. And one more thing I didn't mention is the learning rate here is 3e-4, which is a pretty good default for most optimizations that you want to run at a very early debugging stage. So this is our simple inner loop, and we are overfitting a single batch, and this looks good. So now what comes next is we don't just want to overfit a single batch, we actually want to do an optimization. So we actually need to iterate these XY batches and create a little data loader that makes sure that we're always getting a fresh batch and that we're actually optimizing a reasonable objective. So let's do that next. Okay, so this is what I came up with, and I wrote a little data loader light. So what this data loader does is we're importing the token up here. We're reading the entire text file from this single input.txt, tokenizing it, and then we're just printing the number of tokens in total and the number of batches in a single epoch of iterating over this dataset. So how many unique batches do we output before we loop back around to the beginning of the document and start reading it again? So we start off at position 0, and then we simply walk the document in batches of b times t. So we take chunks of b times t and then always advance by b times t. And it's important to note that we're always advancing our position by exactly b times t. But when we're fetching the tokens, we're actually fetching from current position to b times t plus 1. And we need that plus 1 because remember, we need the target token for the last token in the current batch. And so that way we can do the XY exactly as we did it before. And if we are to run out of data, we'll just loop back around to 0. So this is one way to write a very, very simple data loader that simply just goes through the file in chunks and is good enough for us for current purposes. And we're going to complexify it later. And now we'd like to come back around here, and we'd like to actually use our data loader. So the import tick token has moved up, and actually all of this is now useless. So instead we just want a train loader for the training data, and we want to use the same hyperparameters for 4. So batch size was 4 and time was 32. And then here we need to get the XY for the current batch. So let's see if Copilot gets it, because this is simple enough. So we call the next batch, and then we make sure that we have to move our tensors from CPU to the device. So here, when I converted the tokens, notice that I didn't actually move these tokens to the GPU. I left them on the CPU, which is the default. And that's just because I'm trying not to waste too much memory on the GPU. In this case, this is a tiny data set and it would fit, but it's fine to just ship it to GPU right now for our purposes right now. So we get the next batch, we keep the data loader simple CPU class, and then here we actually ship it to the GPU and do all the computation. And let's see if this runs. So Python train GPT2.py. And what do we expect to see before this actually happens? what we expect to see is now we're actually getting the next batch. So we expect to not overfit a single batch. And so I expect our loss to come down, but not too much. And that's because I still expect it to come down because in the 50,257 tokens, many of those tokens never occur in our dataset. So there's some very easy gains to be made here in the optimization by, for example, taking the biases of all the logits that never occur and driving them to negative infinity. And that would basically it's just that all of these crazy Unicodes or different languages, those tokens never occur, so their probability should be very low. And so the gains that we should be seeing are along the lines of basically deleting the usage of tokens that never occur. That's probably most of the loss gain that we're going to see at this scale right now. But we shouldn't come to a zero because we are only doing 50 iterations, and I don't think that's enough to do an epoch right now. So let's see what we got. We have 338,000 tokens, which makes sense with our 3-to-1 compression ratio because there are 1 million characters. So one epoch with the current setting of B and T will take 2,600 batches. And we're only doing 50 batches of optimization in here. So we start off in a familiar territory as expected, and then we seem to come down to about 6.6. So basically, things seem to be working okay right now with respect to our expectations. So that's good. Okay, next, I want to actually fix a bug that we have in our code. It's not a major bug, but it is a bug with respect to how GPT-2 training should happen. So the bug is the following. We were not being careful enough when we were loading the weights from Hugging Face, and we actually missed a little detail. So if we come here, notice that the shape of these two tensors is the same. So this one here is the token embedding at the bottom of the transformer, right? So, and this one here is the language modeling head at the top of the transformer. And both of these are basically two-dimensional tensors, and their shape is identical. So here, the first one is the output embedding, the token embedding, and the second one is this linear layer at the very top, the classifier layer. Both of them are of shape 50,257 by 768. This one here is giving us our token embeddings at the bottom, and this one here is taking the 768 channels of the transformer and trying to upscale that to 50,257 to get the logis for the next token. So they're both the same shape, but more than that, actually, if you look at comparing their elements, in PyTorch, this is an element-wise equality, so then we use .all, and we see that every single element is identical. And more than that, we see that if we actually look at the data pointer, this is a way in PyTorch to get the actual pointer to the data and the storage. We see that actually the pointer is identical. So not only are these two separate tensors that happen to have the same shape and elements, they're actually pointing to the identical tensor. So what's happening here is that this is a common weight tying scheme that actually comes from the original Attention is All You Need paper, and actually even the reference before it. So if we come here, embeddings and softmax in the Attention is All You Need paper, they mentioned that in our model, we shared the same weight matrix between the two embedding layers and the pre-softmax linear transformation similar to 30. So this is an awkward way to phrase that these two are shared and they're tied and they're the same matrix. And the 30 reference is this paper. So this came out in 2017. And you can read the full paper, but basically it argues for this weight tying scheme. And I think intuitively the idea for why you might want to do this comes from this paragraph here. And basically you can observe that you actually want these two matrices to behave similar in the following sense. If two tokens are very similar semantically, like maybe one of them is all lowercase and the other one is all uppercase, or it's the same token in a different language or something like that, if you have similarity between two tokens, presumably you would expect that they are nearby in the token embedding space. But in the exact same way, you'd expect that if you have two tokens that are similar semantically, you'd expect them to get the same probabilities at the output of a transformer because they are semantically similar. And so both positions in the transformer at the very bottom and at the top have this property that similar tokens should have similar embeddings or similar weights. And so this is what motivates their exploration here. And they kind of, I don't want to go through the entire paper, and you can go through it, but this is what they observe. They also observe that if you look at the output embeddings, they also behave like word embeddings. If you just kind of try to use those weights as word embeddings. So they kind of observe this similarity, they try to tie them, and they observe that they can get much better performance in that way. And so this was adopted in the attention is all you need paper, and then it was used again in GPT-2 as well. So I couldn't find it in the transformers implementation. I'm not sure where they tie those embeddings, but I can find it in the original GPT-2 code introduced by OpenAI. So this is OpenAI GPT-2 source model. And here where they are forwarding this model, and this is in TensorFlow, but that's okay, we see that they get the WTE token embeddings. And then here is the encoder of the token embeddings and the position. And then here at the bottom, they use the WTE again to do the logits. So when they get to logits, it's a matmul of this output from the transformer, and the WTE tensor is reused. And so the WTE tensor basically is used twice on the bottom of the transformer and on the top of the transformer. And in the backward pass, we'll get gradients contributions from both branches, right? And these gradients will add up on the WTE tensor. So we'll get a contribution from the classifier layer, and then at the very end of the transformer, we'll get a contribution at the bottom of it, floating again into the WTE tensor. So we are currently not sharing WTE in our code, but we want to do that. So weight sharing scheme. And one way to do this, let's see if Copilot gets it. Oh, it does. Okay. So this is one way to do it. Basically, relatively straightforward. What we're doing here is we're taking the WTE.weight and we're simply redirecting it to point to the LM head. So this basically copies the data pointer, right? It copies the reference. And now the WTE.weight becomes orphaned, the old value of it, and PyTorch will clean it up. Python will clean it up. And so we are only left with a single tensor, and it's going to be used twice in the forward pass. And this is, to my knowledge, all that's required. So we should be able to use this, and this should probably train. We're just going to basically be using this exact same sensor twice. And we weren't being careful with tracking the likelihoods, but according to the paper and according to the results, you'd actually expect slightly better results doing this. And in addition to that, one other reason that this is very, very nice for us is that this is a ton of parameters, right? What is the size here? It's 768 times 50,257. So this is 40 million parameters. And this is a 124 million parameter model. So 40 divided 124. So this is like 30% of the parameters are being saved using this weight tying scheme. And so this might be one of the reasons that this is working slightly better. If you're not training the model long enough, because of the weight tying, you don't have to train as many parameters. And so you become more efficient in terms of the training process because you have fewer parameters and you're putting in this inductive bias that these two embeddings should share similarities between tokens. So this is the weight tying scheme, and we've saved a ton of parameters, and we expect our model to work slightly better because of this scheme. Okay, next, I would like us to be a bit more careful with the initialization and to try to follow the way GPT-2 initialized their model. Now, unfortunately, the GPT-2 paper and the GPT-3 paper are not very explicit about initialization, so we kind of have to read between the lines. And instead of going to the paper, which is quite vague, there's a bit of information in the code that OpenAI released. So when we go to the model.py, we see that when they initialize their weights, they are using the standard deviation of 0.02. And that's how so this is a normal distribution for the weights, and the standard deviation is 0.02. For the bias, they initialize that with 0. And then when we scroll down here, why is this not scrolling? The token embeddings are initialized at 0.02, and position embeddings as 0.01 for some reason. So those are the initializations, and we'd like to mirror that in GPT-2 in our module here. So here's a snippet of code that I sort of came up with very quickly. So what's happening here is at the end of our initializer for the GPT module, we're calling the apply function of NN module, and that iterates all the submodules of this module and applies init weights function on them. And so what's happening here is that we're iterating all the modules here, and if they are an nn.linear module, then we're going to make sure to initialize the weight using a normal with a standard deviation of 0.02. If there's a bias in this layer, we will make sure to initialize that to 0. Note that 0 initialization for the bias is not actually the PyTorch default. By default, the bias here is initialized with a uniform, so that's interesting. So we make sure to use 0. And for the embedding, we're just going to use 0.02 and keep it the same. So we're not going to change it to 0.01 for positional because it's about the same. And then if you look through our model, the only other layer that requires initialization and that has parameters is the layer norm. And the PyTorch default initialization sets the scale in the layer norm to be 1 and the offset in the layer norm to be 0. So that's exactly what we want, and so we're just going to keep it that way. And so this is the default initialization if we are following the the GPT-2 source code that they released. I would like to point out, by the way, that typically the standard deviation here on this initialization, if you follow the Javier initialization, would be 1 over the square root of the number of features that are incoming into this layer. But if you'll notice, actually, 0.02 is basically consistent with that, because the D model sizes inside these transformers for GPT-2 are roughly 768, 1600, etc. So 1 over the square root of, for example, 768 gives us 0.03. If we plug in 1600, we get 0.02. If we plug in 3 times that, it's 0.014, etc. So basically 0.02 is roughly in the vicinity of reasonable values for these initializations anyway. So it's not completely crazy to be hard coding 0.02 here, but you'd like typically something that grows with the model size instead, but we will keep this because that is the GPT-2 initialization per their source code. But we are not fully done yet on initialization because there's one more caveat here. So here, a modified initialization which accounts for the accumulation on the residual path with model depth is used. We scale the weight of residual layers at initialization by a factor of 1 over square root of n, where n is the number of residual layers. So this is what GPT-2 paper says. So we have not implemented that yet, and we can do so now. Now, I'd like to actually kind of like motivate a little bit what they mean here, I think. So here's roughly what they mean. If you start out with zeros in your residual stream, remember that each residual stream is of this form where we continue adding to it. X is X plus something, some kind of contribution. So every single block of the residual network contributes some amount, and it gets added. And so what ends up happening is that the variance of the activations in the residual stream grows. So here's a small example. If we start at 0, and then we, for 100 times, we have sort of this residual stream of 768 zeros. And then 100 times we add random, which is a normal distribution, 0 mean, 1 standard deviation. If we add to it, then by the end, the residual stream has grown to have standard deviation of 10. And that's just because we're always adding these numbers. And so this scaling factor that they use here exactly compensates for that growth. So if we take n and we basically scale down every one of these contributions into the residual stream by 1 over the square root of n. So 1 over the square root of n is n to the negative 0.5, right? Because n to the 0.5 is the square root, and then 1 over the square root is n negative 0.5. If we scale it in this way, then we see that we actually get 1. So this is a way to control the growth of activations inside the residual stream in the forward pass. And so we'd like to initialize in the same way, where these weights that are at the end of each block, so this cproj layer, the GPT paper proposes to scale down those weights by 1 over the square root of the number of residual layers. So one crude way to implement this is the following. I don't know if this is PyTorch sanctioned, but it works for me, is we'll do in the initialization, see that special nano GPT scale init is 1. So we're setting kind of like a flag for this module. There must be a better way in PyTorch, right? But I don't know. Okay, so we're basically attaching this flag and trying to make sure that it doesn't conflict with anything previously. And then when we come down here, this std should be 0.02 by default. But then if has utter module of this thing, then std times equals, Copilot is not guessing correctly. So we want 1 over the square root of the number of layers. So the number of residual layers here is twice times self.config layers, and then this times -0.5. So we want to scale down that standard deviation, and this should be correct and implement that. I should clarify, by the way, that the 2 times number of layers comes from the fact that every single one of our layers in the transformer actually has 2 blocks that add to the residual pathway, right? We have the attention and then the MLP. So that's where the 2 times comes from. And the other thing to mention is that what's slightly awkward, but we're not going to fix it, is that because we are weight sharing the WTE and the LM head, in this iteration over all submodules, we're going to actually come around to that tensor twice. So we're going to first initialize it as an embedding with 0.02, and then we're going to come back around it again in a linear and initialize it again using 0.02. And it's going to be 0.02 because the LM head is, of course, not scaled, so it's not going to come here. It's going to be basically initialized twice using the identical same initialization, but that's okay. And then scrolling over here, I added some code here so that we have reproducibility to set the seeds, and now we should be able to Python train GPT-2.py and let this running. And as far as I know, this is the GPT-2 initialization in the way we've implemented it right now. So this looks reasonable to me. Okay, so at this point, we have the GPT-2 model. We have some confidence that it's correctly implemented. We've initialized it properly, and we have a data loader that's iterating through data batches, and we can train. So now comes the fun part. I'd like us to speed up the training by a lot, so we're getting our money's worth with respect to the hardware that we are using here. And we're going to speed up the training by quite a bit. Now, you always want to start with what hardware do you have, what does it offer, and are you fully utilizing it? So in my case, if we go to NVIDIA SMI, we can see that I have 8 GPUs, and each one of those GPUs is an A100 SXM 80 gigabytes. So this is the GPU that I have available to me in this box. Now, when I use to spin up these kinds of boxes, by the way, my favorite place to go to is Lambda Labs. They do sponsor my development and that of my projects, but this is my favorite place to go. And this is where you can spin up one of these machines and you pay per hour, and it's very, very simple. So I like to spin them up and then connect VS Code to it, and that's how I develop. Now, when we look at the A100s that are available here, A100 80 gigabyte SXM is the GPU that I have here. And we have a bunch of numbers here for how many calculations you can expect out of this GPU. So when I come over here and I break in right after here, so Python train GPT. So I'm breaking in right after we calculate the logits and the loss. And the interesting thing I'd like you to note is when I do logits.dtype, this prints torch.float32. So by default in PyTorch, when you create tensors, and this is the case for all the activations and for the parameters of the network and so on, by default, everything is in float32. That means that every single number, activation or weight and so on, is using a float representation that has 32 bits. And that's actually quite a bit of memory. And it turns out empirically that for deep learning as a computational workload, this is way too much. And deep learning and the training of these networks can tolerate significantly lower precisions. Not all computational workflows can tolerate small precision. So for example, if we go back to the data sheet, you'll see that actually these GPUs support up to FP64. And this is quite useful, I understand, for a lot of scientific computing applications. And there they really need this, but we don't need that much precision for deep learning training. So currently we are here, FP32, and with this code as it is right now, we expect to get at most 19.5 teraflops of performance. That means we're doing 19.5 trillion operations, floating point operations. So this is floating point multiply, add, most likely. And so these are the floating point operations. Now notice that if we are willing to go down in precision, so TF32 is a lower precision format, we're going to see in a second, you can actually get an 8x improvement here. And if you're willing to go down to float 16 or bfloat 16, you can actually get times 16x performance, all the way to 312 teraflops. You see here that NVIDIA likes to cite numbers that have an asterisk here. This asterisk says with sparsity, but we are not going to be using sparsity in our code, and I don't know that this is very widely used in the industry right now, so most people look at this number here without sparsity. And you'll notice that we could get even more here, but this is int 8, and int 8 is used for inference, not for training, because int 8 has a it basically has uniform spacing, and we actually require a float so that we get a better match to the normal distributions that occur during training of neural networks, where both activations and weights are distributed as a normal distribution. And so floating points are really important to match that representation. So we're not typically using int 8 for training, but we are using it for inference. And if we bring down the precision, we can get a lot more teraflops out of the tensor cores available in the GPUs. We'll talk about that in a second. But in addition to that, if all of these numbers have fewer bits of representation, it's going to be much easier to move them around. And that's where we start to get into the memory bandwidth and the memory of the model. So not only do we have a finite capacity of the number of bits that our GPU can store, but in addition to that, there's a speed with which you can access this memory. And you have a certain memory bandwidth. It's a very precious resource. And in fact, many of the deep learning workloads for training are memory bound. And what that means is actually that the tensor cores that do all these extremely fast multiplications, most of the time they're waiting around, they're idle, because we can't feed them with data fast enough. We can't load the data fast enough from memory. So typical utilizations of your hardware, if you're getting 60% utilization, you're actually doing extremely well. So half of the time in a well-tuned application, your tensor cores are not doing multiplies because the data is not available. So the memory bandwidth here is extremely important as well. And if we come down in the precision for all the floats, all the numbers, weights and activations suddenly require less memory. So we can store more and we can access it faster. So everything speeds up and it's amazing. And now let's reap the benefits of it. And let's first look at the TensorFloat 32 format. Okay, so first of all, what are tensor cores? Well, tensor core is just an instruction in the A100 architecture, right? So what it does is it does basically a little 4x4 matrix multiply. So this is just matrix multiplication here of 4x4 matrices. And there are multiple configurations as to what precision any of these matrices are, in what precision the internal accumulate happens, and then what is the output precision, input precisions, etc. So there's a few switches, but it's basically a 4x4 multiply. And then anytime we have any operations that require matrix multiplication, they get broken up into this instruction of little 4x4 multiply. And so everything gets broken up into this instruction because it's the fastest way to multiply matrices. And it turns out that most of the computational work that we're doing up above, all of it really is matrix multiplication. Most of the work computationally happens in the linear layers, linear, etc. There's a few things sandwiched in between. So there's some additions in residuals, there's some Galou nonlinearities, there's some layer norms, etc. But if you just time them, you'll see that these are nothing. Like basically, the entire transformer is just a bunch of matrix multiplications, really. And especially at this small scale, 124 million parameter model, actually the biggest matrix multiplication by far is the classifier layer at the top. That is a massive matrix multiply of going from 768 to 50,257. And that matrix multiply dominates anything else that happens in that network, roughly speaking. So it's matrix multiplies that become a lot faster, which are hidden inside our linear layers. And they're accelerated through tensor cores. Now, the best reference I would say for tensor cores is basically just go to the A100 architecture white paper, and then it's pretty detailed, but I think it's like relatively readable mostly if you half understand what's happening. So figure 9, tensor float 32. So this is the explanation basically for TF32 and what happens here. And you see that there's many configuration options here available. So the input operands and what precisions are they in, the accumulator, and basically the internal representation within the instruction when you do the accumulate of this matrix multiplication. So the intermediate plus equals of the intermediate little vector multiplies here, that all happens in FP32. And then this is an 8x improvement, as I mentioned, to the ops that we get. So TF32 specifically, we're looking at this row here. And the way this works is normally FP32 has 32 bits. TF32 is the exact same bits. We have 1 sign bit, we have 8 exponent bits, except the mantissa bits get cropped in the float. And so basically we end up with just 19 bits instead of 32 bits, because the last 13 bits get truncated, they get dropped. And all of this is internal to the instruction. So none of it is visible to anything in our PyTorch. None of our PyTorch code will change. All of the numbers will look identical. It's just that when you call the tensor core instruction internally in the hardware, it will crop out these 13 bits, and that allows it to calculate this little matrix multiply significantly faster, 8x faster. Now, of course, this speed up comes at a cost, and the cost is that we are reducing the precision. Our accumulate is still in FP32, our output is FP32, our inputs are FP32, but internally things get truncated in the operands to perform the operation faster, and so our results are starting to be a bit more approximate. But empirically, when you actually train with this, you basically can't tell the difference. So the reason I like TF32 is because if you can tolerate a little bit of a precision fudge, then this is free. Like, none of your code sees this. It's fully internal to the operation, and the operation to you just goes 8x faster, and it's a bit more approximate. And so it's a pretty sweet spot, I would say, in optimization. And let's see what that looks like first. So I've set up our code to just time the iterations. So import time. I changed the hyperparameters so that we have something a bit more that reflects kind of workload that we want to run, because we want to do a fairly large run at the end of this. So let's use batch size 16, and let's now use the actual GPT-2 maximum sequence length of 1024 tokens. So this is the configuration. And then for 50 iterations, I'm just doing something very lazy here. I'm doing time.time to get the current time. And then this is the optimization loop. And now I want to time how long this takes. Now, one issue with working with GPUs is that as your CPU, when your CPU runs, it's just scheduling work on GPU. It's ordering some work, right? And so it sends a request and then it continues running. And so it can happen sometimes that we sort of speed through this and we queue up a lot of kernels to run on the GPU. And then the CPU sort of like gets here and takes time, but actually the GPU is still running because it takes it time to actually work through the work that was scheduled to run. And so you're just building up a queue for the GPU. And so actually if you want to wait, trošku data synchronize, and this will wait for the GPU to finish all the work that was scheduled to run up above here, and then we can actually take the time. So basically we're waiting for the GPU to stop this iteration, takes time, and then we're going to just print it. So here I'm going to run the training loop, and here on the right I'm watching NVIDIA SMI. So we start off at 0, we're not using the GPU, And then by default, PyTorch will use GPU 0, so we see that it gets filled up. And we're using 35 gigabytes out of 80 gigabytes available. And then here on the left, we see that because we've cranked up the batch size, now it's only 20 batches to do a single epoch on our tiny Shakespeare. And we see that we're seeing roughly 1,000 milliseconds per iteration here, right? So the first iteration sometimes is slower, and that's because PyTorch might be doing a lot of initializations here on the very first iteration. And so it's probably initializing all these tensors and buffers to hold all the gradients. And I'm not 100% sure all the work that happens here, but this could be a slower iteration. When you're timing your logic, you always want to be careful with that. But basically, we're seeing 1,000 milliseconds per iteration. And so this will run for roughly 50 seconds as we have it right now. So that's our baseline in Float32. One more thing I wanted to mention is that if this doesn't fit into your GPU and you're getting out of memory errors, then start decreasing your batch size until things fit. So instead of 16, try 8 or 4 or whatever you need to fit the batch into your GPU. And if you have a bigger GPU, you can actually potentially get away with 32 and so on. By default, you want to basically max out the batch size that fits on your GPU. And you want to keep it nice numbers. So use numbers that have lots of powers of 2 in them. So 16 is a good number, 8, 24, 32, 48. These are nice numbers, but don't use something like 17 because that will run very inefficiently on the GPU. And we're going to see that a bit later as well. So for now, let's just stick with 16, 1024. And the one thing that I added also here, and I ran it again, is I'm calculating tokens per second throughput during training, because we might end up changing the batch size around over time, but tokens per second is the objective measure that we actually really care about. How many tokens of data are we training on, and what is the throughput of tokens that we're getting in our optimization? So right now we're processing and training on 163,000 tokens per second roughly, and that's a bit more objective metric. Okay, so let's now enable TF32. Now, luckily, PyTorch makes this fairly easy for us. And to enable TF32, you just need to do a single line, and it's this. And when we go to the PyTorch documentation here for this function, basically this tells PyTorch what kind of kernels to run. And by default, I believe it is highest precision for matmul. And that means that everything happens in Float32, just like it did before. But if we set it to high, as we do right now, matrix multiplications will now use TensorFloat 32 when it's available. My GPU is the A100, so it's an Ampere series, and therefore TF32 is available. If you have an older GPU, this might not be available for you. But for my GPU, it's available. And so what I expect PyTorch to do is that every single place where we see an nn.linear, inside there's a matrix multiplication, and I expect that matrix multiplication now to be running on tensor cores, utilizing the TF32 precision. So this is the single line of change that is, I believe, necessary, and let's rerun this. Now we saw that in terms of the throughput that is promised to us, we're supposed to be getting 8x roughly. So let's see what happens. And that 8x came from here, right? 8x, and it also came from looking at it here, 156 T-flops instead of 19.5. Okay, so what actually happened? So we're seeing that our throughput roughly 3x'd, not 8x'd. So we're from 1000 milliseconds, we're going down to 300 milliseconds, and our throughput is now about 50,000 tokens per second. So we have a roughly 3x instead of 8x. So what happened? And basically what's happening here is, again, a lot of these workloads are memory bound. And so even though the TF32 offers, in principle, a lot faster throughput, all of these numbers everywhere are still Float32s. And it's Float32 numbers that are being shipped all over the place through the memory system, and it's just costing us way too much time to shuttle around all this data. And so even though we've made the multiply itself much faster, we are memory bound, and we're not actually seeing the full benefit that would come from this napkin math here. That said, we are getting a 3x faster throughput, and this is free. Single line of code in PyTorch. All your variables are still Float32 everywhere. It just runs faster, and it's slightly more approximate but we're not going to notice it basically. So that's TF32. Okay, so let's now continue. So we've exercised this row, and we saw that we can crop out some of the precision inside the operation itself. But we saw that we're still memory bound. We're still moving around all these floats, right? Otherwise, and we're paying that cost because of this. So let's now decrease the amount of stuff that we're going to be moving around. And we're going to do that by dropping down to B float 16. So we're only going to be maintaining 16 bits per float. And we're going to use the B float 16. I'll explain in a bit FP16 difference. And we're going to be in this row. So when we go back to the documentation here for the A100, we see here the precisions that are available. And this is the original FP32. The TF32 crops out the precision. And then here in BF16, you see that it is very similar to TF32, but it's even more aggressive in cropping off of the precision, the mantissa of this float. So the important thing with B float 16 is that the exponent bits and the sign bit, of course, remain unchanged. So if you're familiar with your float numbers, and I think this should probably be an entire video by itself, the exponent sets the range that you can represent of your numbers. And the precision is how much precision you have for your numbers. And so the range of numbers is identical, but we have fewer possibilities within that range because we are truncating the mantissa, so we have less precision in that range. But what that means is that things are actually fairly nice because we have the original range of numbers that are representable in float, but we just have less precision for it. And the difference with FP16 is that they actually touch and change the range. So FP16 cannot represent the full range of FP32. It has a reduced range. And that's where you start to actually run into issues because now you need these gradient scalars and things like that. And I'm not going to go into the detail of that in this video because that's a whole video by itself. But FP16 actually historically came first. That was available in the Volta series before Ampere. And so FP16 came first and everyone started to train in FP16, but everyone had to use all these gradient scaling operations, which are kind of annoying, and it's an additional source of state and complexity. And the reason for that was because the exponent range was reduced in FP16. So that's the IEEE FP16 spec. And then they came out with BF16 and the Ampere. And they made it much simpler because we're just truncating mantissa, we have the exact same range, and we do not need gradient scalars. So everything is much, much simpler. Now, when we do use BF16 though, we are impacting the numbers that we might be seeing in our PyTorch code. This change is not just local to the operation itself. So let's see how that works. There's some documentation here so I think this is probably the best page to explain how to use mixed precision in PyTorch. Because there are many other tutorials and so on, even within PyTorch documentation, that are a lot more confusing. And so I recommend specifically this one because there's 5 other copies that I would not recommend. And then when we come here, ignore everything about everything, ignore everything about gradient scalars, and only look at torch.autocast. And basically, also this comes to a single line of code at the end. So this is the context manager that we want. And we want to use that in our network. When you click into the torch.autocast, autocasting, it has a bit more guideline for you. So it's telling you do not call bfloat16 on any of your tensors, just use autocast and only surround the forward pass of the model and the loss calculation. And that's the only 2 things that you should be surrounding. Leave the backward and the optimizer step alone. So that's the guidance that comes from the PyTorch team. So we're going to follow that guidance. And for us, because the loss calculation is inside of the model forward pass for us, we are going to be doing this. And then we don't want to be using torch float 16 because if we do that, we need to start using gradient scalars as well. So we are going to be using B float 16. This is only possible to do in Ampere. But this means that the changes are extremely minimal, like basically just this one line of code. Let me first break in to here before we actually run this. So right after logits, I'd like to show you that different from the TF32 that we saw, this is actually going to impact our tensors. So this logis tensor, if we now look at this and we look at the D type, we suddenly see that this is now B float 16. It's not float 32 anymore. So our activations have been changed. The activations tensor is now B float 16, but not everything has changed. So model.transformer .wte, this is the weight token embedding table. It has a .weight inside it, and the D type of this weight, this parameter, is still torch float 32. So our parameters seem to still be on float 32, but our activations, the logits, are now in B float 16. So clearly, this is why we get the mixed precision. Some things PyTorch is keeping in float 32, some things PyTorch is converting to lower precision. And what gets converted at what point is not super clear. I remember scrolling down, is it here? Blah. Okay, I can't find it. I thought it was here. Okay, there we go. So there are a few docs on when you're using this autocast, what gets converted to bfloat 16 and when. So for example, only these matrix multiply like operations get converted to bfloat 16, but a lot of operations remain in float 32. So in particular, a lot of normalizations like layer norms and things like that, not all of those layers might be converted. So only some layers selectively would be running bfloat 16, but things like softmax, layer norms, log softmax, so loss function calculations, a lot of those things might remain in float 32 because they are more susceptible to precision changes. Matrix multiplies are fairly robust to precision changes. So some parts of the network are impacted more or less by the precision change. So basically only some parts of the model are running in reduced precision. Let's take it for a spin and let's actually see what kind of improvement we achieve here. Okay, so we used to be 333 milliseconds, we're now 300. And we used to be somewhere around 50,000 tokens per second, we're now 55. So we're definitely running faster, but maybe not a lot faster. And that's because there are still many, many bottlenecks in our GPT-2. We're just getting started. But we have dropped down the precision as far as we can with my current GPU, which is A100. We're using PyTorch Autocast. Unfortunately, I don't actually exactly know what PyTorch Autocast does. I don't actually know exactly what's in bfloat 16, what's in float 32. We could go in and we could start to scrutinize it. But these are the kinds of rules that PyTorch has internally, and unfortunately, they don't document it very well. So we're not going to go into that in too much detail. But for now, we are training in bfloat 16. We do not need a gradient scaler. And the reason things are running faster is because we are able to run tensor cores in bfloat 16 now. That means we are in this row, but we are also paying in precision for this. So we expect slightly less accurate results with respect to the original FP32. But empirically, in many cases, this is a worth it kind of trade-off because it allows you to run faster, and you could, for example, train longer and make up for that precision decrease. So that's bfloat 16 for now. Okay, so as we can see, we are currently at about 300 milliseconds per iteration, and we're now going to reach for some really heavy weapons in the PyTorch arsenal, and in particular, we're going to introduce torch.compile. So torch.compile is really quite incredible infrastructure from the PyTorch team, and it's basically a compiler for neural networks. Like, it's almost like GCC for C and C++ code. This is just the GCC of neural nets. So came out a while ago and extremely simple to use. The way to use torch compile is to do this. It's a single line of code to compile your model and return it. Now this line of code will cost you compilation time, but as you might guess, it's going to make the code a lot faster. So let's actually run that because this will take some time to run. But currently, remember, we're at 300 milliseconds and we'll see what happens. Now, while this is running, I'd like to explain a little bit of what torch.compile does under the hood. So feel free to read this page of PyTorch. But basically, there's no real good reason for you to not use torch compile in your PyTorch. I kind of feel like you should be using it almost by default if you're not, unless you're debugging and you want your code to run really fast. And there's one line here in torch compile that I found that actually kind of like gets to why this is faster. Speed up mainly comes from reducing Python overhead and GPU read writes. So let me unpack that a little bit. Okay, here we are. Okay, so we went from 300 milliseconds. We're now running at 129 milliseconds. So this is 300 divided 129, about 2.3x improvement from a single line of code in PyTorch. So quite incredible. So what is happening? What's happening under the hood? Well, when you pass the model to Torch compile, what we have here in this NN module, this is really just the algorithmic description of what we'd like to happen in our network. And Torch compile will analyze the entire thing, and it will look at what operations you'd like to use. And with the benefit of knowing exactly what's going to happen, it doesn't have to run in what's called the eager mode. It doesn't have to just kind of like go layer by layer, like the Python interpreter normally would start at the forward, and the Python interpreter will go, okay, let's do this operation, and then let's do that operation. And it kind of materializes all the operations as it goes through. So these calculations are dispatched and run in this order. And the Python interpreter and this code doesn't know what kind of operations are going to happen later. But Torch compile sees your entire code at the same time, and it's able to know what operations you intend to run, and it will kind of optimize that process. The first thing it will do is it will take out the Python interpreter from the forward pass entirely, and it will kind of compile this entire neural net as a single object with no Python interpreter involved. So it knows exactly what's going to run, it will just run that, and it's all going to be running in efficient code. The second thing that happens is this read-write that they mentioned very briefly. So a good example of that, I think, is the GELU nonlinearity that we've been looking at. So here we use the NN GELU. Now this here is me basically just breaking up the NN GELU, which you remember has this formula. So this here is the equivalent implementation to what's happening inside GELU. Algorithmically, it's identical. Now, by default, if we're using this instead of NN.GELU here, what would happen without Torch compile? Well, the Python interpreter would make its way here, and then it would be, okay, well, there's an input. Well, let me raise this input to the third power, and it's going to dispatch a kernel that takes your input and raises it to the third power, and that kernel will run. And when this kernel runs, what ends up happening is this input is stored in the memory of the GPU. So here's a helpful example of the layout of what's happening, right? You have your CPU. This is in every single computer. There's a few cores in there, and you have your RAM, your memory. And the CPU can talk to the memory, and this is all well known. But now we've added the GPU. And the GPU is a slightly different architecture, of course. They can communicate. And it's different in that it's got a lot more cores than a CPU. All of those cores are individually a lot simpler too. But it also has memory, right? This high bandwidth memory. I'm sorry if I'm botching it. HBM. I don't even know what that stands for. I'm just realizing now. But this is the memory, and it's very equivalent to RAM, basically, in the computer. And what's happening is that input is living in the memory. And when you do input cubed, this has to travel to the GPU, to the cores, and to all the caches and registers on the actual chip of this GPU. And it has to calculate all the elements to the third, and then it saves the result back to the memory. And it's this travel time that actually causes a lot of issues. So here, remember this memory bandwidth? We can communicate about 2 terabytes per second, which is a lot, but also we have to traverse this link and it's very slow. So here on the GPU, we're on chip and everything is super fast within the chip. But going to the memory is extremely expensive, takes extremely long amount of time. And so we load the input, do the calculations, and load back the output. And this round trip takes a lot of time. And now right after we do that, we multiply by this constant. So what happens then is we dispatch another kernel, and then the result travels back, all the elements get multiplied by a constant, and then the results travel back to the memory. And then we take the result and we add back input. And so this entire thing again travels to the GPU, adds the inputs, and gets written back. So we're making all these round trips from the memory to actually where the computation happens, because all the tensor cores and the ALUs and everything like that is all stored on the chip in the GPU. So we're doing a ton of round trips, and PyTorch, without using Torch compile, doesn't know to optimize this because it doesn't know what kind of operations you're running later. You're just telling it, raise the power to the third, then do this, then do that, and it will just do that in that sequence. But Torch Compile sees your entire code. It will come here and it will realize, wait, all of these are element-wise operations. And actually, what I'm going to do is I'm going to do a single trip of input to the GPU. Then for every single element, I'm going to do all of these operations while that memory is on the GPU, or chunks of it, rather. And then I'm going to write back a single time. So we're not going to have these round trips. And that's one example of what's called kernel fusion, and is a major way in which everything is sped up. So basically, if you have your benefit of hindsight and you know exactly what you're going to compute, you can optimize your round trips to the memory, and you're not going to pay the memory bandwidth cost. And that's fundamentally what makes some of these operations a lot faster, and what they mean by read writes here. So let me erase this because we are not using it. And yeah, we should be using Torch Compile, and our code is now significantly faster, and we're doing about 125,000 tokens per second. But we still have a long way to go. Before we move on, I wanted to supplement the discussion a little bit with a few more figures, because this is a complicated topic, but it's worth understanding on a high level what's happening here. And I could probably spend an entire video of like 2 hours on this, but just a preview of that basically. So this chip here, that is the GPU. This chip is where all the calculations happen mostly. But this chip also does have some memory in it. But most of the memory by far is here in the high bandwidth memory, HBM, and is connected. They're connected, but these are two separate chips basically. Now here, this is a zoom in of kind of this cartoon diagram of a GPU. And what we're seeing here is, number one, you see this HBM. I realize it's probably very small for you, but on the sides here it says HBM. And so that's the links to the HBM. Now the HBM is, again, off chip. On the chip, there are a large number of these streaming multiprocessors. Every one of these is an SM. There's 120 of them in total. And this is where a lot of the calculations happen. And this is a zoom in of a single individual SM. It has these 4 quadrants, and see, for example, Tensor Core. This is where a lot of the matrix multiply stuff happens, but there's all these other units to do all different kinds of calculations for FP64, FP32, and for integers and so on. Now, so we have all this logic here to do the calculations, but in addition to that, on the chip, there is memory sprinkled throughout the chip. So L2 cache is some amount of memory that lives on the chip. And then on the SMs themselves, there's L1 cache. I realize it's probably very small for you, but this blue bar is L1. And there's also registers. And so there is memory stored here, but the way this memory is stored is very different from the way memory is stored in HBM. This is a very different implementation using, in terms of like what the silicon looks like, it's a very different implementation. So here you would be using transistors and capacitors, and here it's a very different implementation with SRAM and what that looks like. But long story short is there is memory inside the chip, but it's not a lot of memory. That's the critical point. So this is an example diagram of a slightly different GPU, just like here, where it shows that, for example, typical numbers for CPU DRAM memory, which is this thing here, you might have 1 terabyte of disk, right? But it would be extremely expensive to access, especially for a GPU. You have to go through the CPU here. Now, next we have the HBM. So we have tens of gigabytes of HBM memory on a typical GPU here, but it's, as I mentioned, very expensive to access. And then on the chip itself, everything is extremely fast within the chip, but we only have a couple 10 megabytes of memory collectively throughout the chip. And so there's just not enough space because the memory is very expensive on the chip. And so there's not a lot of it, but it is lightning fast to access in relative terms. And so basically, whenever we have these kernels, the more accurate picture of what's happening here is that we take these inputs, which live by default on the global memory, and now we need to perform some calculation. So we start streaming the data from the global memory to the chip. We perform the calculations on the chip and then stream it back and store it back to the global memory, right? And so if we don't have Torch Compile, we are streaming the data through the chip doing the calculations and saving to the memory, and we're doing those round trips many, many times. But if it's Torch compiled, then we start streaming the memory as before. But then while we're on the chip, we have a chunk of the data that we're trying to process. So that chunk now lives on the chip. While it's on the chip, it's extremely fast to operate on. So if we have kernel fusion, we can do all the operations right there in an element-wise fashion. And those are very cheap. And then we do a single round trip back to the global memory. So operator fusion basically allows you to keep your chunk of data on the chip and do lots of calculations on it before you write it back. And that gives huge savings. And that's why Torch Compile ends up being a lot faster, or that's one of the major reasons. So again, just a very brief intro to the memory hierarchy and roughly what Torch Compile does for you. Now, Torch Compile is amazing, but there are operations that Torch Compile will not find. And an amazing example of that is flash attention, to which we turn next. So flash attention comes from this paper from Stanford in 2022. And it's this incredible algorithm for performing attention. So, and running it a lot faster. So flash attention will come here and we will take out these 4 lines, and flash attention implements these 4 lines really, really quickly. And how does it do that? Well, flash attention is a kernel fusion operation. So you see here we have in this diagram, they're showing PyTorch, and you have these 4 operations. They're including dropout, but we are not using dropout here. So we just have these 4 lines of code here. And instead of those, we are fusing them into a single fused kernel of flash attention. So it's a kernel fusion algorithm, but it's a kernel fusion that Torch Compile cannot find. And the reason that it cannot find it is that it requires an algorithmic rewrite of how attention is actually implemented here in this case. And what's remarkable about it is that flash attention actually, if you just count the number of flops, flash attention does more flops than this attention here. But flash attention is actually significantly faster. In fact, they cite 7.6 times faster potentially. And that's because it is very mindful of the memory hierarchy as I described it just now. And so it's very mindful about what's in high bandwidth memory, what's in the shared memory, and it is very careful with how it orchestrates the computation such that we have fewer reads and writes to the high bandwidth memory. And so even though we're doing more flops, the expensive part is their load and store into HBM, and that's what they avoid. And so in particular, they do not ever materialize this n by n attention matrix, this ATT here. Flash attention is designed such that this matrix never gets materialized at any point, and it never gets read or written to the HBM. And this is a very large matrix, right? So because this is where all the queries and keys interact, and we're sort of getting, for each head, for each batch element, we're getting a T by T matrix of attention, which is a million numbers, even for a single head at a single batch index. So basically this is a ton of memory, and this is never materialized. And the way that this is achieved is that basically the fundamental algorithmic rewrite here relies on this online softmax trick, which was proposed previously, and I'll show you the paper in a bit. And the online softmax trick, coming from a previous paper, shows how you can incrementally evaluate a softmax without having to sort of realize all of the inputs to the softmax to do the normalization. And you do that by having these intermediate variables m and l, and there's an update to them that allows you to evaluate the softmax in an online manner. Now flash attention, actually, so recently flash attention 2 came out as well, so I have that paper up here as well. That has additional gains to how it calculates flash attention. And the original paper that this is based on basically is this online normalizer calculation for softmax. And remarkably, it came out of NVIDIA, and it came out of it like really early, 2018. So this is 4 years before flash attention. And this paper says that we propose a way to compute the classical softmax with fewer memory accesses, and hypothesize that this reduction in memory accesses should improve softmax performance on actual hardware. And so they are extremely correct in this hypothesis. But it's really fascinating to me that they're from NVIDIA and that they had this realization, but they didn't actually take it to the actual flash attention. That had to come 4 years later from Stanford. So I don't fully understand the how this happened historically, but they do basically propose this online update to the softmax right here. And this is fundamentally what they reuse here to calculate the softmax in a streaming manner. And then they realize that they can actually fuse all the other operations with the online softmax calculation into a single fused kernel, flash attention, and that's what we are about to use. So a great example, I think, of being aware of memory hierarchy, the fact that flops don't matter, the entire memory access pattern matters, and that torch compile is amazing, but there are many optimizations that are still available to us that potentially torch compile cannot find. Maybe one day it could, but right now it seems like a lot to ask. So here's what we're going to do. We're going to use flash attention, and the way to do that basically in PyTorch is we are going to comment out these 4 lines, and we're going to replace them with a single line. And here we are calling this compound operation in PyTorch called scaled.product attention. And PyTorch will call flash attention when you use it in this way. I'm not actually 100% sure why torch compile doesn't realize that these 4 lines should just call flash attention in this exact way. We have to do it again for it, which in my opinion is a little bit odd, but here we are. So you have to use this compound up, and let's wait for a few moments before torch compile gets around to it. And then let's remember that we achieved 6.05661. I have it here. That's the loss we were expecting to see. And we took 130 milliseconds before this change. So we're expecting to see the exact same result by iteration 49, but we expect to see faster runtime because flash attention is just an algorithmic rewrite and it's a faster kernel, but it doesn't actually change any of the computation, and we should have the exact same optimization. So, okay, so we're a lot faster. We're at about 95 milliseconds, and we achieved 6.058. Okay, so they're basically identical up to a floating point fudge factor. So it's the identical computation, but it's significantly faster, going from 130 to roughly 96. And so this is 96 divide 130-ish. So this is maybe 27-ish% improvement. Really interesting, and that is flash attention. Okay, we are now getting to one of my favorite optimizations, and it is simultaneously the dumbest and the most brilliant optimization, and it's always a little bit surprising to me. Anyway, so basically I mentioned a few minutes ago that there are some numbers that are nice and some numbers that are ugly. So 64 is a beautiful, nice number. 128 is even nicer. 256 is beautiful. What makes these numbers beautiful is that there are many powers of 2 inside them. You can divide by 2 many times. And examples of ugly numbers are like 13 and 17 and something like that. Prime numbers, numbers that are not even, and so on. And so pretty much you always want to use nice numbers in all of your code that deals with neural networks or CUDA, because everything in CUDA works in sort of like powers of 2, and lots of kernels are written in terms of powers of 2, and there are lots of blocks of sizes 16 and 64 and so on. So everything is written in those terms, and you always have special case handling for all kinds of logic that when your inputs are not made of nice numbers. So let's see what that looks like. Basically, scan your code and look for ugly numbers is roughly the heuristic. So 3 times is kind of ugly. I'm not 100% sure. Maybe this can be improved, but this is ugly and not ideal. 4 times is nice, so that's nice. 1024 is very nice. That's a power of 2. 12 is a little bit suspicious. Not too many powers of 2. 768 is great. 50,257 is a really, really ugly number. It's, first of all, it's odd. So and there's not too many powers of 2 in there. So this is a very ugly number, and it's highly suspicious. And then when we scroll down, all these numbers are nice. And then here we have mostly nice numbers except for 25. So in this configuration of GPT-2 XL, a number of heads is 25. That's a really ugly number. That's an odd number. And actually, this did cause a lot of headaches for us recently when we were trying to optimize some kernels to run this fast, and required a bunch of special case handling. So basically, these numbers are, we have some ugly numbers, and some of them are easier to fix than others. And in particular, the vocab size being 50,257, that's a very ugly number, very suspicious, and we want to fix it. Now, when you fix these things, one of the easy ways to do that is you basically increase the number until it's the nearest power of 2 that you like. So here's a much nicer number. It's 50,304. And why is that? Because 50,304 can be divided by 8 or by 16 or by 32, 64. It can even be divided by 128, I think. Yeah, so it's a very nice number. So what we're going to do here is, this is the GPT config, and you see that we initialize vocab size to 50,257. Let's override just that element to be 50,304. Okay, so everything else stays the same. We're just increasing our vocabulary size. So we're adding, it's almost like we're adding fake tokens. So that vocab size has powers of 2 inside it. Now, actually what I'm doing here, by the way, is I'm increasing the amount of computation that our network will be doing. If you just count the flops on, like, do the math of how many flops we're doing, we're going to be doing more flops. And we still have to think through whether this doesn't break anything. But if I just run this, let's see what we get. Currently, this ran in maybe 96.5 milliseconds per step. I'm just kind of like eyeballing it. And let's see what kind of a result we're going to get. While this is compiling, let's think through whether our code actually works okay when we increase the vocab size like this. Let's look at where vocab size is actually used. So we swing up to the init, and we see that it's used inside the embedding table, of course, so all the way at the bottom of the transformer, and it's used at the classifier layer, all the way at the top of the transformer, so in 2 places. And let's take a look, and we're running at 93. So 93 milliseconds instead of 96.5. So we are seeing a roughly 4% improvement here by doing more calculations. And the reason for this is we've made an ugly number into a nice number. I'm going to come into the explanation for that a little bit again, but for now, let's just convince ourselves that we're not breaking anything when we do this. So first of all, we've made the WTE, the embedding table for the tokens, we've made it larger. It's almost like we introduced more tokens at the bottom. And these tokens are never used because the GPT tokenizer only has tokens up to 50,256. And so we'll never index into the rows that we've added. So we're wasting a little bit of space here by creating memory that's never going to be accessed, never going to be used, etc. Now that's not fully correct because this WTE weight ends up being shared and ends up being used in the classifier here at the end. So what is that doing to the classifier right here? Well, what that's doing is we're predicting additional dimensions at the classifier now, and we're predicting probabilities for tokens that will, of course, never be present in the training set. And so therefore, the network has to learn that these probabilities have to be driven to 0. And so the logits that the network produces have to drive those dimensions of the output to negative infinity. But that's no different from all the other tokens that are already in our dataset, or rather that are not in our dataset. So Shakespeare only probably uses, let's say, 1,000 tokens out of 50,257 tokens. So most of the tokens are already being driven to 0 probability by the optimization. We've just introduced a few more tokens now that in a similar manner will never be used and have to be driven to 0 in probability. So functionally, though, nothing breaks. We're using a bit more extra memory, but otherwise this is a harmless operation as far as I can tell. And we're adding calculation, but it's running faster. And it's running faster because, as I mentioned in CUDA, so many kernels use block tiles, and these block tiles are usually nice numbers, so powers of 2. So calculations are done in like chunks of 64 or chunks of 32. And when your desired calculation doesn't neatly fit into those block tiles, there are all kinds of boundary kernels that can kick in to like do the last part. So basically, in a lot of kernels, they will truncate up your input and they will do the nice part first, and then they have a whole second phase where they come back to anything that like remains, and then they process the remaining part. And the kernels for that could be very inefficient. And so you're basically spinning up all this extra compute, and it's extremely inefficient. So you might as well pad your inputs and make it fit nicely. And usually that empirically ends up actually running faster. So this is another example of a 4% improvement that we've added. And this is something that also Torch Compile did not find for us. You would hope that Torch Compile at some point could figure an optimization like this out. But for now, this is it. And I also have to point out that we're using PyTorch nightly, So that's why we're only seeing 4%. If you're using PyTorch 2.3.1 or earlier, you would actually see something like 30% improvement just from this change, from changing it to from 50,000 to 57 to 5304. So again, one of my favorite examples also of having to understand the under the hood and how it all works, and to know what kinds of things to tinker with to push the performance of your code. Okay, so at this point we have